Hey everyone, thanks for coming to check out Python Glasgow. Tonight is a bit of an experiment for the group, so I'm very interested in hearing your feedback and we can see what we can change for the future. Firstly, of course, we have this video on YouTube which you found, that is the main content, and in the description down below you will find a link to the meetup event page, and there will be a link to both Zoom and Slack. We're going to be using both of these tonight, so Zoom will be active before and after this video is playing, if you want to have some FaceTime and catch up with some of the other members. And then we'll be using Slack for the same, but also during the talk you can use it for discussing or linking things that are relevant, or asking questions for the speakers. As both of the speakers have pre-recorded their videos, you can't ask questions in real time, but you can speak to them in Slack while they are presenting, which is one of the neat advantages of this format. Yeah, so tonight we have two talks. After we have an in-between, we'll have a short break. The second talk will be by Mark, and he's going to help us get started with MongoDB. First, however, Erry is going to talk to us about FastAPI. Please give them a warm welcome.
Hi everyone, my name is Erry. I am a senior software engineer for a startup called Langtum, and it's a health tech company with a mission to save the NHS £1 billion. And today I'm going to speak about FastAPI, and I will talk about what sort of advantages it brings, as well as show a simple how-to. So FastAPI is an async await based API framework. That means it's more meant about building APIs than more monolithic applications. So it does not include like any views or templating. It does not come with its own ORM, but it can be integrated with any ORM or no ORM. If your project does not require it, no need to add it. And it's built on top of Python 3 standards, such as I mentioned, async await, data classes, and type hinting. And it's quite young, version 0.61.1. So although I found that it works really well, there can be breaking changes between versions, since the API is still quite young and not even version 1 yet. So async await, you may know, is a new Python feature which allows you to run more than one I/O task concurrently, which basically is quite helpful, like if you're building an API, which is something that is more I/O heavy than, like, say, CPU heavy. You can have more than one asynchronous network request going off at any one time, which makes it quite a lot faster and more performant than synchronous frameworks such as Django. So you can see some benchmarks that have already been done, and you can see that FastAPI is like the fourth fastest Python framework, and it's only slower than Uvicorn, API Hour, and Starlet, which are all quite low level. And it's actually built on top of Uvicorn and Starlet, so of course it would not be as fast as they are. And it's actually on par with Express.js in Node.js, which is really good performance in my opinion. It's very easy to get started with. You can see that in order to have a basic hello world page, you literally only need those 5 lines of code. And as long as you have FastAPI installed, you have your APIs just started and working. So there's not that much boilerplate for the simple cases. And it basically magically documents itself. If you write your code correctly, it will be documented automatically. So as you can see, for an example, this comes with OpenAPI, or previously called Swagger UI, and you can see that you get the different URLs that are available and the parameters and the example response for them. And it comes with automatic validation. So if you give a number when you should be, or give a string when you should be given an integer, for example, you will automatically get an error without having to write a lot of boilerplate validation code. And it's very easy to write tests for, even if you are using the async features that it comes with. So in order to demonstrate how easy it is, I wanted to show a simple example, which shows some like banking or financial transactions that the user can do. And you can have, basically, we will be returning a list of transactions through the API. So first of all, I made a hard-coded route in my API. You can see that I've just created a router object. And I said, when you get the transactions, just return a hard-coded list of ID to. That's just to test that the route works. And then I imported and included my route with another, like, just 2 lines of code to import it. And you can see that now when I navigated to my API, there was already documentation for my new route that I just added through the Open API. So again, just by including the route, it was automatically documented. I didn't need to try to do anything. And when I try to do the request, I get back the response of ID2, which was hard-coded. So that's good. It means that my API is working. So now I wanted to add like a database actually, so that the transactions are not just hard-coded, but they are returned from a SQLite database. And I also used SQL Alchemy just as an example of how you may integrate with an ORM if you want to, even though again it's not required. So I've imported SQL Alchemy like normal, and I've set up the database URL. And what you may see that's a bit different, I'm using the databases module and saying that my database is an instance of this databases module, which is not normally something that you do with SQLite or with SQL Alchemy rather, excuse me. The reason why I have imported this module, which you would maybe not normally see, is that it provides like an asyncio wrapper on top of SQLite or Postgres or some other types of databases, and it basically allows you to do SQL queries using async and await, and it basically abstracts away any sort of extra setup that you would have to do. It also handles connection pooling and stuff like that, so you don't have to worry about it. So basically it makes async await painless and pretty much baked in for your databases. But that's the only like weird line of code that you would normally see. And then I make my SQL Alchemy models. Not going to go into depth, but basically it's just a table with transactions, ID, description, string, amount, float, and just creating the tables, setting up the engine correctly, and then just exposing this these tables to my application. And here you can see some more extra code that I've added, which is FastAPI specific. So FastAPI has events that it emits. So on startup, it emits a startup event, which connects to the database. And on shutdown, we can disconnect from the database. And you can see here it's async and await. As I said, the database module provides this async and await wrapper on top of the SQLite connection. So I've said, let's include my transactions router again, and this time I'm passing in the databases. And here, instead of hard coding the transactions, I'm just saying await. Again, you can see that it's all asynchronous. Database.fetch all a query, and it comes back with all the transactions that are in this database. So then you have the Sorry, yeah. So we can see that if you call the API, you get back the transactions from the database, so that works. But if you look at the API documentation as it is now, you will see that it actually says that there's no example available, and there's no schema to show like the format of the output. So like if you saw earlier, I was talking about automatic documentation, and you would be able to see like what the different data that actually is returned by the API is. So how do we make that happen? Like, where is it? Do you need to do something? Well, you need to do a small thing. So FastAPI is based on top of pedantic models for documentation and for data validation as well. So it's not like your SQL Alchemy models, you still need those, but you can think of them as classes that describe the data that can be inserted into your API or the data that your API returns. And you could see that as extra boilerplate, but actually it not only helps you document the input and output and do validation painlessly, but also it helps your editor with like type hinting, because if you use something like VS Code, you can see that like transactions have the specified API when they come in or when they come out. So it's a bit of extra code, but I think it makes everything much easier in the long term. And you can see that all I've had to do was import the base pedantic model and then extend it with my transaction. And so we say this is the output of the transactions API. It's ID, description, and amount. It's the same as my SQLite model, but in your code, you could have a different model if you wanted to, that is different from your database. Sort of like using a Django serializer maybe. So now I've just imported my model, you can see in my router, and then all I've had to do was say, hey, the response model is a list of transactions. That's all the code that I had to change in my router. So now when the documentation is generated, it will go and say, I should use this model for the response, and therefore it knows that transactions are the transactions API returns a list of objects, and each object has ID, description, and amount. So just by specifying a Python class and including it in my route, I have automatic documentation. And as I said, this is used for validation as well. So we did not need validation in this route that just returns the transactions. But let's say, for example, you want to be able to get the transaction by ID. So I'm saying, let's specify a route that is transactions/transaction ID. And again, it returns now a single transaction, same as before. And the code, just select something from the table where the ID equals transaction ID. And again, the query is async await because we're using the async await database module. But in here, we're specifying, it takes a transaction ID parameter, and we're specifying using type hinting. Transaction ID is an integer. And you could also have, again, a custom model if you were doing like post requests and inserting or posting data to the server. You could have a more complicated pedantic model like before that specified your input, but now it's just an integer. So just by specifying the type in the function argument, pedantic and FastAPI picks this up, and you see that there's a route transactions ID that was specified, and the path transaction ID is an integer. So it's documented that it's an integer, it does not take any other kind of data, and you can put in the ID and get a single transaction. And you can see that if we open the transactions /2 to get transaction number 2, it returns the transaction just fine. Of course, 2 is a valid number, but if we add like 2a, which is not a number, it's automatically validated. So just by specifying again that this is the type of integer in our API, we get automatic validation of the input data. And again, you could do it with post and have like a whole model of your input data with Pydantic, which again would be validated. And really quickly, I mentioned as well that this is very easy to test. So you have, let's say, a simple PyTest example that checks that the response is correct. Nothing in this code should be particularly amazing if you've seen PyTest, but the only difference is that I've added asyncio decorator, and I've said it's an asynchronous function to get the transactions. So that's one difference, and it needs a specific module installed to work. And then from HTTPX, I've imported an async HTTP client that's an external model that just does gives you easy to use async HTTP requests, and I'm just using it here with my app to get the response, which then I am comparing. So basically, tests are almost exactly the same as you would with any other synchronous API. It's just that I'm using async await and saying that this is an asynchronous test, and I'm using an HTTP client which happens to be asynchronous. So yeah, that's pretty much all that I wanted to show. And in summary, I hope that you have an idea of all the advantages of FastAPI. It's very fast, self-documenting, basically automatically validates your data with just writing some classes and using those Python standards of like type hinting, and using the Pydantic module to check to validate just using those classes. And it allows you to write clean code, and it's extremely easy to use. So I hope that you found the example helpful, and maybe you will use FastAPI in one of your projects. Thank you.
Okay, great. Thank you very much for that talk, Erry. I really enjoyed it. Now we're going to take around about a 5-minute break. We're going to do a bit more looking at the Python Glasgow logo, and then we're going to come back and we'll see Mark's talk. So if you need to go and grab a drink or anything like that, now is a good time. Okay, we are now going to hand over to Mark for our second talk this evening. Thank you, Mark. Take it away.
Hello, everybody. My name's Mark Smith, although I'm known online as GD2K nearly everywhere for reasons that aren't as funny as they might, as you might imagine. I run Python Edinburgh, and I work for MongoDB as a developer advocate. And I'm going to talk to you about how you can get started with MongoDB and Python, which I think is a language that's particularly well suited to working with MongoDB. And hopefully by the end of the talk, you'll agree. So before I get into the depths of working with MongoDB and Python, I thought I should just cover at a high level what MongoDB is. And it's a database server, but it's not designed to run on a single node. It's a cluster database server, so it's designed to run in a cluster of at least 3 machines. And what happens when you bring a cluster of 3 machines together is that they have a little chat with each other and they elect a primary. And the rest become secondaries. And the primary server is the machine that your client will be talking to. All the clients talk to a single primary at any one time. That machine is responsible for handling all the queries you might make of the data, the database, and also for taking any updates and handling those and passing any updated data down to the secondaries. You always talk to the current primary, so it's not for scaling or for performance reasons that you have multiple machines. It's for redundancy. It allows a couple of things. One is that you can get zero downtime upgrades by taking one of the machines out of the cluster, upgrading it, and then putting it back in the cluster again. And you also get redundancy. So if anything happens to one of the machines in the cluster can continue to perform without it. If you don't have enough machines to maintain quorum when one of the machines is down, then the database goes into a read-only state, which is important for ensuring that the data maintains consistency when you do go back to achieving quorum again. Each node in the cluster stores a whole copy of the database. You can do analytics against the secondaries. You can force a connection to the secondaries, but you have to understand that because the data is streamed via the primary, they're not the authority on the data anymore. And so you may be working with slightly stale data. But if that's not a problem, and it often isn't with analytics queries, then you can make use of the fact that they are under less read load than the primary. If spinning up and maintaining a cluster seems like a lot of work, I highly recommend you have a look at MongoDB Atlas, which is our hosted database as a service offering. MongoDB will host your database for you. It also includes backups and some extra features like free text search, charting, serverless functions, and it will scale up and down as required to keep your costs as low as possible. So it can save you money. And on top of all of that, there's a generous free tier. So if you just want to build a prototype of something, or you want to build something small scale for just yourself, MongoDB will host it for free for you. So it's a good way to get started. So it's all very well saying MongoDB is a database, but how does it store data? Well, MongoDB is a document database, so it stores documents that look a bit like this. This is a document from our sample movie database describing a movie called Blacksmith Scene. The full plot is a blacksmith hammering at an anvil, and then he stops and wipes his brow and takes a sip of beer and then goes back to hammering on the anvil again. And it's a 1-minute movie from 1893, which makes it like a YouTube video from 130 years ago, which I think is pretty cool. But I just want to highlight a couple of things about the values in this document. So one thing to point out is that unlike a row in a relational database, some of these values aren't scalar values. This cast value is an array of strings, and the IMDb value is another object, or in MongoDB we call them subdocuments. So you can have a hierarchy as deep as you like within the restriction of a document cannot be bigger than 64 megabytes. So they can get quite rich. They can get quite complex. It's a very rich way to store data, which I'm sure you'll understand if you've worked with sort of big JSON documents before. The other thing I'd like to point out is that it stores some values that aren't supported by JSON. It's got an object ID here as the first value, and then further down there's a datetime value. This is represented as a Python datetime value, but what it's indicating is that MongoDB is storing it as a native kind of timestamp type. And this is because MongoDB doesn't store JSON. It stores BSON, which is a binary data representation. And it's a more efficient way of storing structured data than JSON, but it's important to MongoDB because it's not just how MongoDB stores data. Queries are also written as BSON documents, so we're going to be looking at quite a few of them, admittedly represented as Python dicts in this talk. And BSON is also how requests and responses are passed between MongoDB clients and the MongoDB cluster. So it's actually the network protocol that's used to talk to MongoDB. So it is everywhere. BSON is similar to JSON as a structured document format. Key value pairs have an order, which is something that isn't necessarily obvious when working with dictionaries in various languages. And it also supports these extra types like object ID, timestamp values, various integral and floating point types, and an efficient binary blob type, if those are useful to you. So now getting into the Python side of things, we actually have two drivers for Python. One is the slightly older PyMongo driver, which is a blocking driver that works more the way you might expect if you've worked with database drivers over the years. If you're making a request to the database, you call a function in the driver, it goes off to the database, and you're waiting until it gets some data back and then hands you back a cursor. Motor is a more recent driver. It's async compatible. It works with both asyncio and Tornado. But there is something that's worth knowing about Motor, which is that under the hood, it is not a native asyncio driver. It's not fully async. Under the hood, it is actually, it runs PyMongo in a background thread. So it's just a wrapper. It is, however, a production quality driver fully supported by MongoDB, so you shouldn't be afraid to use it, and you'll need to use it if you're writing async applications. So before moving into a whole load of examples of data and queries, it's worth introducing the data set that I'll be working with. So this is how I've been coping with lockdown under the COVID-19 pandemic. This is a photo that I tweeted a few months ago that I thought was quite funny. And the truth isn't entirely different to this. It's just that I usually only have about 2 or 3 of these bottles out at a time because I have been teaching myself how to make cocktails. This is a Negroni and an espresso martini, and the one on the right is not actually one that I've made. It's a bacon-infused whiskey old-fashioned that I had in a bar in New York just before lockdown hit in February. And I've been, while I've been learning to make cocktails and adapting recipes a little bit, I've compiled many of them into a Google Doc. But a Google Doc is a terrible way to store a list of recipes, and I work for a database company, so they have to go into a database. So here is a schema for a cocktail recipe database. This is a single document I would like to store. This is a recipe for a Negroni Spagliato, which is a variation of a Negroni, but with the gin replaced by Prosecco, which makes it a bit lighter and bubbly. It was invented by a bartender in Milan, apparently, who was particularly busy one day and accidentally grabbed a bottle of Prosecco and poured it into the Negroni before he realized that it wasn't gin. And when they tasted it, they realized it was an improvement, perhaps, on a Negroni, and so the Negroni Spagliato was born. Spagliato is the Italian for messed up, so it's a messed up Negroni. But to look at the sort of general structure of this database, to sort of design our schema, I'm going to translate this into some Python type annotations. We're not going to use the class that I'm going to define, but I just want to sort of consolidate in your mind what these documents look like so that when I show you some queries, you can understand the kind of thing that it's doing behind the scenes. So the first 3 items are all scalar values. We have an object ID and 2 strings. That's not super interesting. Ingredients is a little bit more complex. In fact, it's the most complex field in this document. So this is an array of subdocuments. And I can tell you that all of those subdocuments kind of have the same format, the same schema. So I'm going to define a type for that called ingredient. So really, this is a list of ingredients. So let's just kind of define it that way. And then the last block, instructions, is like that but simpler. So it's a list of strings. So that's simple enough. And I've just realized I've made a mistake by typing string out in full there, but there we go. Just ignore that. And then I've also added a class below for ingredient. Again, not going to use these classes, but I just wanted to show you that actually the structure is relatively straightforward. So we've got ingredients, which is a list of ingredient documents, and everything else is kind of everything else we're going to be working with is basically a scalar value. As well as my recipes collection, I also have a review collection, which stores documents that relate to people kind of clicking on a review, stars on a web page. So rating is a value from 1 to 5, and recipe ID is the ID value of a recipe document that this rating relates to. So now this is the Python code for connecting to a MongoDB cluster. If you're working with Atlas, you'll have a URI that represents your cluster. If you're working with your own cluster, you may provide it with more data about the machines in your cluster. But fundamentally, it's not. You will know, if you have a MongoDB cluster, you will know how to connect to it. So you pass those details into a Mongo client constructor, hands you back a client instance. MongoDB cluster can contain multiple databases. Here, I'm obtaining the cocktails database and storing it away in a variable. And then finally, I get one of the collections out of the database called recipes and put that away in a recipes variable. So just to reiterate, because we're going to be using recipes quite a lot, the recipes variable is a collection object. And so it has multiple methods for obtaining data from that collection. And here is one way you can use that collection object. I can call insert1. I can pass it my document, which is just represented as dicts and things. So PyMongo will handle converting this to BSON for you and then pass it to the database as BSON, and then the database will store it away. And it returns a kind of summary object that would hopefully say that it's inserted one document into recipes, and it will also hand you back the ID of the document that you've just inserted. That's not hugely interesting, and even less interesting really than the cocktail itself, which was just water. Another point of the whole CRUD thing is being able to find recipes in the database, and you do those by calling find on the collection object. So here I'm calling find. I'm not passing it a query, so I'm not filtering out any documents, and that returns a cursor, and the cursor conceptually contains all of the documents in the collection. So if in the loop beneath, it's just an iterable. So if you loop through the documents in the cursor, you get all of the recipes one by one in the database. They're streamed in batches of 100 from the server to the client, so it's not like it's going to overload memory if you just deal with them one by one. If, however, you pass cursor to a list constructor, it will load them all into memory into a single list, and if you've got a huge database, that may crash your machine. It might be useful to loop through all of the documents in a collection, but more usually you will be filtering on certain values. And you do this by passing a query to the find function. A query, again, is a BSON document. And here is a query that says, I want essentially all the documents where name is Negroni Spagliato, which hopefully is just one document in the recipes database. And again, you get a cursor, you can loop through the cursor, you can do whatever you like with the dictionaries that you are returned. Just to reiterate, this is BSON database data in the database, but it will hand you back native Python types for everything that it can. So it automatically converts between a BSON document and a dict, or BSON arrays and lists, and timestamps as date times, etc. If it's you've got a type that is BSON specific, like object ID, that is a type that's defined in the BSON package that you get with PyMongo. Something that's maybe not completely obvious is that documents are more complex than table rows. And so you need a more complex query language for querying within a collection. The complexity of SQL comes because you're defining relationships across collections. It's those relationships that add the complexity to SQL generally. With MongoDB, instead, we tend to be asking questions of things deep within the structure of a document. And so you need a language for being able to do that. The query on the bottom here, matching on the data on the top, is searching within the ingredients array, and it's running the elem match operator, which queries items in an array. And so you pass it this value to elem match, which is a query. Essentially, it's saying name equals vodka. And elem match will match on all the items in an array where that is true. And if any of them are true, your query has returned true. You can combine these various operations as well. There's and or and various other operations that you can combine together to make really quite complex queries constructed as these hierarchical documents. Here, because I'm looking for name equals vodka, and there are no ingredients where name is vodka in the Negroni Spagliato, Negroni Spagliato would be filtered out of this query. You wouldn't be getting it back in your results. But I don't want to talk about queries in any more detail. I said we've got a rich query language for that. I've given you 2 examples. It's an important thing to be able to query using MongoDB query language, but it's not specifically unique to MongoDB. It's not that interesting. I could teach you all the operators, but you probably don't want to sit and watch a talk on that. So I'm going to take a slight sidestep into a feature called aggregation pipelines. There's this feature in MongoDB called the aggregation framework, which is really a different way of querying your database. It allows you to summarize groups of documents. It allows you to join across collections and many other things. It's a way of querying and updating documents in MongoDB. Now, a bit like find, you call a method on a collection to run an aggregation pipeline. In this case, you run the aggregate function on a collection object. And then what happens is, conceptually, all of the documents in recipes are passed through the pipeline. This call that I'm showing you on the screen is an empty pipeline. And so, in fact, this is just the same as calling find without a query. You get back all the documents unchanged. But there are various stages you can add to that pipeline that will either modify individual documents by adding or removing fields. You can filter out documents. You can aggregate documents together and return the resulting kind of merged document. There's a whole load of operations that you can conduct within an aggregation pipeline. And we're going to run through a couple of simpler ones. And I'm going to show you this in MongoDB Compass, because the language itself is, it's a little bit overwhelming at first because it's these nested data structures. And I think MongoDB Compass has this great feature called the aggregation pipeline builder that allows you to build these things semi-visually. And I'm just going to hide myself on the screen for a moment so that I can show you what this interface looks like. So we build an aggregation pipeline. You build the stages going down this middle column. So each stage has its own row, and then across the screen you get previews of the output from each stage. Now this is kind of stage 0, which is really just all of the documents in the collection, and so it's just showing you what the documents look like in the collection before they're passed into the pipeline. So now if you add a stage, you can pick an operation. So stage type, this is the match stage type. And a match stage type is equivalent to calling find on a collection. So I can just pass this, the query that I showed you before, filtering on cocktails that have a vodka ingredient. So this is just taking the vodka cocktails. So the input to this is all of the recipes, and the output from this stage is all the recipes that have vodka in them. And then we can add a second stage, in this case, a lookup stage. And the lookup stage will look up data in another collection. So this is essentially the equivalent to a SQL join. So look up these parameters that I'm passing to this lookup stage say, I want to look up some data in the reviews collection where my local field ID, my primary key, matches the foreign document's recipe ID. And then I want to take all those records, those documents, and I want to embed them in the result as reviews. So that's the name of the new field that we've just created. And so to expand on one of these previews on the right-hand side, what you get is a new reviews field, because that's what I said I wanted it to be called. And that is an array of review documents that have been taken from the reviews collection. So hopefully you recognize the data that's in there from kind of the data that I showed you earlier in the reviews column. So this is how we do a join in MongoDB. So I take those 2 stages together, one after the other. The first is filtering for just vodka cocktails. And now I'm taking all those vodka cocktails and I'm adding the related reviews to them. This is what that looks like visually. So an aggregation pipeline takes all of the documents in a collection. They get passed to the first stage that filters out so everything that's not a vodka cocktail, and then they get passed to the lookup stage that annotates it or sort of extends each of those documents with the related reviews. And because that's the end of the pipeline, those would then get passed to you as your client, as in the cursor. Now, this isn't Python code, but fortunately, Compass supports exporting to Python by clicking on this very small gray button at the top. That then previews the query in Python, and then you can click on this green button over here, which will stick it in your clipboard, and then you can paste it into your Python code. And that's what that sort of graphical pipeline looks like as Python code. Once you've got that, you can do more stuff. Like you can keep on adding stages until you've got the result that you want. So I could add a step to summarize the ratings that we just brought in. So we have an array of ratings called reviews, and I can average those using the add fields stage, which adds a rating field, which is calculated by the average of the reviews ratings. And then I could add a step to sort by the rating, and then I could take the first 5 records, and that gives me the 5 highest rated vodka cocktails in the database. And you might then stick that in a web page. Aggregation pipelines are very powerful. Behind the scenes, they do a whole load of clever stuff as well. They will use indexes whenever that's possible. They will rearrange stages in the pipeline if that's more efficient. There's a lot of stuff in the framework that you don't know is happening. So you can work with them relatively naively. Don't try to prematurely optimize them because the engine is probably smarter at what it's doing than you are. And you can also use aggregation pipelines, as I mentioned before, to update your collections. If you use a set stage, you can use that to create a new collection or to update documents in a collection based on the calculations that you've done within MongoDB. Outside of aggregation pipelines, CRUD operations in MongoDB are very simple. And that leads people to skip the design step. But while you can work on a small scale with bad design, as you get more load and more data, it will cause problems. MongoDB offers MongoDB University courses that are free to really get into each of the topics about database design and index usage to understand them properly. And so I really recommend you check those out if you're planning to use MongoDB in production, because learning these things early on means you're not going to make some of the more basic schema design mistakes that then may cause you problems further down the line when you've got larger data sets or more users. For example, in this database, this collection, I wouldn't have 2 collections for this. I would store the reviews inside the recipe document. But I wanted to show you how joins worked. So I didn't do that. But there's some considerations here about whether you include them in the document. But generally, if you're going to be querying data together, so if I'm going to be, if every time I show a recipe on the screen, I'm going to want to show the ratings with it, then I should generally include the reviews with the document data. If you can't do that, then you have the ability to look up data in other collections, as I showed you. MongoDB also supports transactions, even in sharded clusters now. So you can use those 2 features to make sure that your data is updated and obtained transactionally. The reason for keeping data together, as well as just semantically data goes together and MongoDB can support hierarchical data, is really because document updates are atomic. So you don't have to replace a document in the database. You can update part of a document using these atomic commands. So here is an update 1 call on a collection where it looks up the Negroni Spagliato. Like ideally, that would be an ID rather than just a name that might be duplicated. And then it runs the push operation on it. Now you can have multiple operations that will be conducted on a document. Push just happens to be one of them. All of the update commands that you pass in one call to update 1 will be executed atomically, so they either all succeed or all fail. And you've got commands like push. In this case, I'm adding a review to the reviews field in the recipe document. There's also commands for incrementing, for setting values, and various other things you might want to do with data in your document. So now, having covered kind of queries and updates and things like that, I just wanted to cover one lesser known feature of MongoDB, and that's change streams. Change streams can be summarized really by the watch command. You can call watch on a collection or a database. And what that will do, at least in PyMongo, is it blocks until some data has changed in the database, at which point the database knows you're watching and it will push you the update. And then you will receive this update document that tells you what's changed in the database. So I called this and then replaced one of the records in the database, and I got this update document. So what this is basically saying is this document has changed. Here's the new document details. I've removed some of the details because it was just too much information. But this is essentially all the information you need to write triggers, except because it's running in your client code, it's the ability to write triggers in your favorite programming language with whatever libraries you might want available to you, and to run on any machine you particularly want to run the triggers on. So it really gives you this very powerful kind of underlying tool for responding to changes in your data. And I think it's kind of cool. I've written a chat service with this before where two users in using WebSockets are watching on the same document in a collection. And when any message is inserted into that collection, it's displayed in the screen as HTML. And it was really just a few lines of code. The most complicated thing was kind of the front end JavaScript, kind of getting that to display, than actually just handling these real-time updates to the database. It works particularly well with Motor, with the async driver, because that's just designed to have a whole bunch of things happening in parallel. With PyMongo, you would need to run this in a background thread or something to make sure that your application could do other stuff while also watching in the background for changes to the database. And now I'd just like to kind of summarize a whole bunch of other MongoDB features that I think deserve to be better known and are all available in the Python driver. So I mentioned that MongoDB doesn't enforce a schema on your documents, but it can. You can associate a JSON schema with a collection, and then that will be your documents will be validated against that before they're inserted into the collection from then on. And the nice thing the feature I really like about this is you can do partial validation. So you don't necessarily have to have all documents conforming exactly with the same schema. But what you can do is say, all of the documents in this collection should have a name that is a string. And then that will ensure that you've got some commonality between the documents in a collection, however much you might want that subset of commonality to be. So I think that's quite powerful. MongoDB also supports sharding intrinsically. You can shard on, this is where you divide your data up and host it in multiple parts of your data in different clusters. It's really designed for vast data sets that cannot conceivably fit on a single machine. But more interestingly is a technique called geopinning, where you shard on the location of the user that will need to access that data. And this means you could have a shard cluster in, say, Asia Pacific and a shard cluster in Europe, and you could ensure that all the European customers' data is automatically stored on the European cluster, and that all the Asia Pacific customers' data is automatically stored in Asia Pacific. And that just reduces latency when requesting data from the cluster, depending on where you are. So that's kind of cool. We've also got field level encryption. This is the ability to encrypt data at rest, actually in transit as well. So you would encrypt the data. The driver will automatically encrypt data based on a key before it's transmitted to the server. So the database server never actually gets to know what data it's storing in certain fields. And this is particularly useful for storing really sensitive data. And it means that if somebody gets into your database server, either physically or across the network, they can't access the most sensitive data that you're storing. If they get into your app server, obviously all bets are off, but it's another level of defense in depth. And it's kind of important for certain GDPR compliance purposes and things. And finally, we've got MongoDB Realm, which is a whole platform for building mobile and desktop apps, which can work offline and sync when they're back online. And unfortunately, I really don't have any more time to go into the detail of that platform, but it's really powerful, and you may find it useful if you're building that kind of application. So with that said, MongoDB is a pretty big and complex product. But it's really powerful if you get to know it properly. And I hope you found this sort of quick summary and dive into a few features of MongoDB to be useful. And if you plan to try it out or you have any more questions, please feel free to follow me at GD2K on Twitter and ask me any questions that you have. Thank you very much.
Okay, thank you, Mark, for speaking to us this evening. It's very much appreciated, and I'm sure we all found that very interesting as well. That actually takes us now to the end of this video, really. There will still be some chat going, starting in Zoom now and continuing for a while until it starts to fizzle out. And Slack will remain active for as long as Slack remains active. I encourage people to pop in now and then between meetups as well, because there's often someone around to help if you have any Python questions or just want to chat. Yeah, thanks everyone, and we'll see you next time.